For our project, we are exploring strategies and techniques for detecting Twitter bots. So what question are we trying to answer? Can we effectively identify tweets made by bots on Twitter? And how do we go about starting to answer this question? We don't have access to a database of known bot-made tweets, so we'd likely have to make that dataset ourselves. And can we identify what classifier is best for this kind of detection? So let's establish what are Twitter bots. They are automated Twitter accounts that are controlled by bot software. They resemble actions of everyday Twitter users such as liking tweets, retweeting content, replying to tweets, and even tweeting themselves. There are different types of Twitter bots, including spam bots that are designed to flood Twitter with spam messages. There are fake follower bots that are designed to increase the number of followers on a Twitter account. Political bots that are designed to spread political propaganda and misinformation. And commercial bots that are designed to promote products or services. Overall, Twitter bots can have both positive and negative impacts on the platform and its users. Why do we care? It is no secret that Twitter and social media in general has a lot of bots. Having bots on your social media platform is a liability for a company for multiple reasons. They can spread misinformation and sway public opinion. They can engage in fraudulent activities such as spamming, phishing, and scamming. They can harm public safety by spreading hate and inciting violence. In the past, bot detection would be handled manually by staff, but in this project we aim to explore how machine learning can aid in that detection process. The originality of this project. Obviously, every major social media platform has invested many resources into its own automated bot detection systems, but these are highly proprietary in nature and therefore not exposed to public knowledge. There are legitimate reasons to keep these systems secret. For example, if made public, people who create bots may have an easier time bypassing detection. However, this research is novel in that it attempts to both generate the bot-made tweets and detect them in one package. There are two objectives for this project. We first aim to generate convincing fake tweets that would pass as real to the general public. And secondly, we want to use machine learning to successfully classify these fake tweets versus real tweets. For the scope of this project, we will generate 25,000 tweets in the style of various prolific Twitter profiles with high variety in each personal style. We will then collect 25,000 real tweets from the same users using Twitter's API. What will our process be to tackle this project? Firstly, we will figure out what method is best to generate fake tweets. Then we will generate a database of those fake tweets, collect a database of real tweets, combine the databases as a training and testing set, figure out what model is best for handling this type of input, get a baseline accuracy, tweak the model in search of a higher accuracy, and then run the model on our training and testing set. We will have two measures of success, one for each of the objectives. Firstly, are the generated fake tweets convincing to us? And two, does the classifier have a high level of accuracy? The best case scenario is the generated tweets are convincing and we have a high level of accuracy in classification. The worst case scenario, the generated tweets are not convincing and we have a low accuracy in classification. Since we are both crafting part of the dataset and classifying the dataset, there will likely be a natural push and pull to our measure of success. If our generated tweets are very convincing, then the classification will likely have a lower accuracy. If our classification is very accurate, then it's likely our generated tweets are too distinct from real tweets. These are the four different methods of fake tweet generation that we explored. Firstly was Markov chain, which is a more rudimentary approach which uses probabilities of previous sequences of text to predict the next sequence of text. Second was GPT-2, which is a pre-trained model from OpenAI that we could feed the tweets into to fine-tune the already pre-trained model. Thirdly was a recurrent neural network, which generates text based on patterns learned from a large corpus of text data, which would be our tweets, and then by maintaining an internal memory that allows them to remember information from previous time steps. And lastly was hugging tweets, which is pre-trained models on specific Twitter user accounts that uses the Hugging Transforms library, which is a fine-tuned model of GPT-2. So here are some of the examples of the generated fake tweets. You can see the Markov chain. They would kind of use some buzzwords that the Twitter users like to use a lot, but overall would just spew a bunch of nonsense. And then we had the recurrent neural network. Those were a little better, but again, it was still kind of just nonsense, but they would form better thoughts. Then we used the hugging tweets, and these are pre-trained models, so they did most of the legwork, and these obviously are the best, as you can see, and these would form tweets that were definitely passable to the general public. Based on what I showed you on the last slide, it's clear that the method we decided on to generate the tweets was the hugging tweets. We had the most success using these pre-trained models. Hugging tweets uses a pre-trained GPT-2 model, which is then fine-tuned for multiple epochs on the tweets using the Hugging Face Transforms library. There are thousands of these existing models on various Twitter users, but new ones can be trained for any existing Twitter user with enough tweets. You can see the pipeline on the bottom right. You collect the raw data set, which is the tweets, pre-process them, construct a training data set, and use that GPT-2 pre-trained model, which then trains and fine-tunes it. So here's our final data set that we will use for the classification. We chose 25 different users with existing Hugging Tweets models. About 1,000 real tweets were scraped from each user's timelines using Tweepy, which is a Python package, and another 1,000 fake tweets were generated using Hugging Tweets. The Hugging Tweets models require a starting prompt, and these prompts were randomly chosen from the real tweets. We chose the first 3 words and threw out any user ats, so it's between 1 to 3 words, and you could see the 25 different users on the bottom. We aim to get a variety of users that would have a different style in tweeting.
Moving on to the classification models that we used, we first tested SVM. It's old reliable, and but we realized quickly that this was not really going to work with this type of data that we used. It's basically a word blob, and I'm sure there's a great amount of pre-processing that you could do to get it to work with this type of data. We'd have to narrow it down, dummy variables, all sorts of things, but out of the box it was not a good fit. After that we tried convolutional neural networks. That worked a little bit better, but it had basically the same problems as SVM. It was really slow to train, low accuracy out of the box, and again, I'm sure that there's an amount of data pre-processing that we could do to get this one to work better, but out of the box it didn't feel like a good fit. The third model that we tested, and the one that we settled on, was naive Bayes using a bag of words vectorizer. This one worked really well for this type of data. Out of the box, it had a 64.3% accuracy. It was very, very fast to train and test, and it had the best accuracy of any of the models that we had tested so far. But this accuracy is pretty low. It's better than a coin flip, so it's not doing nothing. But we wanted to see if there was anything we could do to get that a little bit higher. It does pass our low, worst case scenario, low accuracy threshold of 60%, but we're going to explore some different things that we tried in order to make it a little bit more accurate. So here's a list of things that we tried to tweak about our model in order to bump up the accuracy a little bit. The first thing that we did was change out the bag of words for a TF-IDF vectorization. but this seemed to decrease the accuracy about 0.5%. The next thing that we tried was switching that out for an ADA boost on the naive Bayes model, and that also had about a 0.5% decrease in accuracy. After that, we tried tweaking the various parameters of these three different models, the alphas, max features, base estimators, the number of estimators for the ensemble and ADA booster, but none of those seemed to really do anything positively. They either decreased performance or kept it exactly the same. Then we tried lemmatizing each entry for the bag of words naive Bayes model, and that decreased the accuracy quite a bit, 54%, barely better than a coin toss. We tried removing stop words. That decreased accuracy a little bit, less than 1%. We tried reversing all the words in each entry. That didn't have any change in accuracy, which we kind of expect because of it's a bag of words naive Bayes model. And then we tried reversing all the letters just to see what would happen, but that also had no change, which was a bit of a surprise. We'll talk about that in the next slide. So at the end of all the tweaking, the text pre-processing, and the parameter changing that we experimented with for the different models, we came to the conclusion that naive Bayes using a bag of words was just the best for this kind of situation. It had the highest accuracy of all the models, and it was very fast with the default parameters and very minimal text pre-processing. The accuracy isn't amazing, it's only 64% change, but it was relatively the best performing. But while we were experimenting with the text pre-processing, we had a pretty good suspicion that reversing all the words in the text entries wouldn't affect accuracy at all. You know, it's a naive Bayes model with a bag of words. But we did think that something would change by reversing all the letters, and it was a bit of a surprise that nothing happened. It was the exact same accuracy. We suspected it would change somewhat, but it didn't do anything different. ADA Boost did seem like it could have potentially outpaced the bag of words. It did start to perform better when we kept giving it more and more estimators for the ensemble, but you know, as you increase the amount of estimators, it slows down the training very, very significantly. It might have outpaced it at some point, but physical resources dictate that we couldn't continue on that way. It doesn't scale well. So here's a quick look at the various classifiers with their corresponding statistics. On the top left, you'll see our best performing model, the naive Bayes, using a bag of words with very minimal text pre-processing. And on the right of that, you'll see that corresponding confusion matrix. Under those, you'll see the TF-IDF implementation of naive Bayes, and on the right of that, you'll see the ADA boost implementation for naive Bayes. And in this test, we used 5,000 estimators for the ADA boost ensemble. If you take a look, though, at the TF-IDF and the ADA boost statistics, the accuracies are identical to the decimal point. But if you look at their other statistics, the precision, recall, and F-scores, you'll notice that the TF-IDF recall for false, or in this case fake tweets, is much higher than its positive recall. And in the ADA boost case, it's the other way around. It has a higher recall on the positive, or detecting real tweets, versus the negative case. So what this says is that these two models might be better in each case if you're trying to err on either side. So TF-IDF implementation might be better if you're trying, if you care more about detecting false tweets or fake tweets, and the ADA boost model might be better if you care more about making sure that tweets are real, that's true. If you'd like to take a little bit more time to look at these, you can pause the video now. So here are the statistics for the various types of text pre-processing that we tried on the naive Bayes bag of words base model that we were using. On the top left, you'll see we tried reversing the position of each word in every text entry. And on the top right, you'll see we tried reversing each character position in each text entry. You'll notice that these two readouts are exactly identical. And if you go back to the previous slide and compare this to the naive Bayes bag of words with no text pre-processing, these two are identical to that one as well. For the reversing of position of every word, we assumed that there would be no change just because it is a bag of words, naive Bayes. But for the reversing of every character, we did expect there to be some kind of change, but that wasn't the case. So that was a bit of a surprise, as we mentioned earlier in the presentation. On the bottom left, you'll see we've tried removing a small list of stop words, but as we added words to the stop word list, I believe this readout test had 8 stop words removed from it. As we added more, the accuracy went down, so we assumed that adding more to the list would just continue to decrease the accuracy. And on the bottom right, we tried lemmatizing the text before we ran it through the naive Bayes bag of words, and that really decreased accuracy. Not completely sure if the lemmatizing worked as intended or if there was some kind of fault in implementation, but this was pretty consistent with the tweaking of the lemmatization call. If you want to take a closer look at these, you can pause the presentation now. So how did we end up doing? Well, the generated tweets that we came up with were fairly convincing to the human eye. They're not perfect, but they do pass the smell test. All in all, we're giving the tweets a score of 8 out of 10 for being convincing. The accuracy of our best classifier, the naive Bayes bag of words, is a little over 64%, which is technically a passing grade given our stated threshold of 60% being low accuracy for anything below it, but it's obviously not amazing. However, to be fair to our classifier, as we noted earlier in the presentation, this is a push and pull situation where the more convincing the tweets are, the harder the classifier is going to have to work to distinguish them. So if we ended up with a high accuracy for our classifier, that probably meant that our tweets weren't very convincing. So, at the end of the day, we ended up somewhere in the middle between our stated worst case and best case scenarios. I think we're trending more towards the best case from the middle, but, the classifier did have some problems. So what are the lessons learned and the room for improvement? First thing we learned was SVMs and CNNs are not the ideal model for this type of data input. Text blobs needs a lot of data pre-processing in order to get anything usable out of them. The next thing that we learned was that reversing the letter in each text entry has absolutely no effect on the accuracy or the precision or recall or F-scores for the bag of words naive Bayes model. That one was a surprise discovery. We did expect that reversing the words would have no effect, but we did expect a small effect, at least reversing each character in the text entries. So for the room for improvement, if we extended our scope, we could analyze the specific quirks that each tweet generation method has, and with that analysis, we might have been able to adjust our data preprocessing to kind of dig into those quirks and exploit them in order to improve the classifier accuracy. But that's outside of the scope and would require a lot more time.